Well, we're moving on now because we've got the fundamentals of trigonometry down. I know we didn't go too far in depth and we really kind of scratched the surface, but some of the trig identities and the circular trigonometry, all that stuff's going to hang around and wait for a future math class. So instead, we're going to move on and we're going to look at squid scenes or scene. Oh, I see a lot of squid scenes here. Yeah, ooh, 20,000 Leagues Under the Sea, the Disney version there. Some squids attacking ships. Hey, you don't see a squid walking down the sidewalk very often. I think artwork inspired by the Jules Verne 20,000 Leagues Under the Sea. And of course, the greatest squid of all time as far as media is concerned, there is Squidward. And so we'll be taking oh wait, it's not squids. Sequences and series. And we'll start out today with sequences. All right, so our learning target, if I give you something in sequence notation, I want you to be able to write out the terms of the sequence. Isn't that exciting? Yay! So a sequence is just a list of numbers, right? But there's a pattern about it. So here are some examples. All right. You'll notice that sometimes I have the ... which means, hey, it goes on forever. We call that an infinite sequence. Or sometimes it just stops, and we call those a finite sequence. Right? So a sequence is a list of numbers, and there is some type of pattern that we can discover about these numbers. All right? So when we talk about the list of numbers, or when we talk about the sequence, we refer to the first number in the list as a sub 1, right? That one's a subscript. And then a sub 2 is the second one. Now, instead of saying sub or subscript each time, I'll probably just refer to them as A1, A2, A3, A4. But just remember that 1, 2, 3, 4 is a subscript. And just a fancy way of saying, hey, the first number, the second number, the third number. So, for example, on that top sequence there, if I requested, hey, what is A5? You'd say, oh, well, A5 is 13. That's because the fifth term in the sequence is 13. Now, most normal people would say the fifth number in the list, but mathematicians would say, oh, it's the fifth term in the sequence. If I look at that next list of numbers, that next sequence, and I ask for A5, you'd say, oh, A5 would be 48 because the fifth term in the sequence is 48. So let's try write the first four terms of each sequence. All right, so I'm going to say, okay, the nth term equals 5n minus 2. Right, there's a little subscript of n, so that means, a sub n. So it's okay, if I want any old number in the sequence, it's given by this little equation. So let's try find the first four terms. Well, what would be the first term? Well, if I want A1, any place I see an n, I got to plug in a 1. So instead of 5 times n, take away 2, I've got 5 times 1, take away 2. Well, 5 times 1 is 5. 5 take away 2 is 3. There is the first term of the sequence. Okay, what's the second term? What is a sub 2? Well, any place I see an n, I got to plug in a 2. 5 times 2 is 10. 10 subtract 2 is 8. So a sub 2 is 8. How about a sub 3? Well, we got to plug in a 3. 5 times 3 is 15. 15 take away 2 is 13. That's the third term. Let's find the fourth term. 5 times 4 is 20. 20 take away 2 is 18. So to answer the question, what are the first 4 terms of the sequence? It's that list of numbers, 3, 8, 13, 18. You say, hey, I see a pattern. It looks like it went up by exactly 5 every time. Interesting. It went up by 5 every time. Okay, let's take a look at another example. Another super duper, really awesome. Come on, example, get up here. Oh, there it is. Okay, the nth number in the list, a sub n, equals, it's going to be a fraction, -1 to the n power in the numerator, 2n minus 1 in the denominator. Okay, so let's plug in the numbers 1, 2, 3, and 4 and get the answers. So if I plug in the number 1, any place I see an n, I got to put a 1. Let's see, -1 to the first power, that's just -1. 2 times 1 is 2. 2 take away 1 is 1. -1 divided by 1. A lot of work just to get down to -1. So that's the first term. Let's find the next one. Any place I have an n, I got to replace it with a 2. Now the numerator, also known as the top of the fraction, -1 squared, well, -1 times -1 is +1. And then the denominator, the bottom, 2 times 2 is 4. 4 take away 1, of course, is 3. 1 over 3, can't do anything with it. That's as simple as it goes. Let's go to the next one. All right, since this is the third term, or the third number in the list, plug in a 3 every place there was an n. Of course, -1 times -1 times -1, that comes out as a -1 up there on top of the fraction. 2 times 3 is 6. 6 take 1 is 5. -1 over 5. Okay, that's wonderful. If I want the fourth number, I got to plug in the number 4 every place I see an n. -1 to the 4th power over 2 times 4 minus 1. Now, -1 to the 4th power, now we're flipped back to a +1. All right, -1 times -1 times -1 times -1, that is a +1. Be very careful if you try to use a calculator, because if you ask -1 to the 4th power, and you do not put the -1 inside parentheses, it's going to do 1 to the 4th power and then stick a negative in front. All right, so be very careful if you want to try to use a calculator for those. And 8 minus 1 is 7. So let's put this list of numbers together. Now again, a normal person would say, hey, look, it's a list of numbers. A mathematician would look, hey, those are the first 4 terms of the sequence. Right? A mathematician will call it a sequence instead of a list. A mathematician will call those terms instead of numbers. Right? Mathematicians are kind of weird. Now, a pattern still emerges. Look how it's flipping back and forth. Negative, positive, negative, positive. And if we kept going, negative, positive, negative, positive, negative, positive. In the bottoms of the fraction, there's a pattern there. Right? There was a 1 that was on the bottom, and then a 3, then a 5, then a 7. So it looks like they flip back and forth between positive and negative. And it looks like the bottom of the fraction is always just going to be the next odd number. Do we have a couple examples, I hope? Aha. A sub n equals 2 to the n power over n factorial. Okay, we got to dust off the memory banks. Hopefully we remember how to play with exponents. And if you've never seen factorial before, well, there's no time like the present to learn how to work with that. Okay, so let's figure out the first number in the list. I'll need 2 to the first power over 1 factorial. 2 to the first power, of course, is just 2. 1 factorial is just 1. Right, that's kind of plain and boring. You're like, well, what's the point of a factorial then? Well, hang on for a couple examples. 2 divided by 1 is plain old 2. That is term number 1. Okay, term number 2. I got to plug in the number 2 every place I had an n. So it is 2 squared in the numerator, 2 factorial in the denominator. Of course, 2 times 2 is going to be 4. So that's what's on top. Now, on the bottom of the fraction, 2 factorial tells me I have to do 2 times 1. 2 times 1 is 2. 4 divided by 2 is 2. So this second term is 2. How about the third term? Well, I'll need 2 to the third power divided by 3 factorial. Okay, 2 times 2 is 4. 4 times 2 is 8. So on top there's an 8. And what does the 3 factorial tell me to do? It tells me to do 3 times 2 times 1. So hopefully you're starting to see the pattern of those factorials, right? 1 factorial was just 1. 2 factorial was 2 times 1. 3 factorial is 3 times 2 times 1. So I've got 8 over 6. That fraction will reduce to 4 over 3. Now, if you're curious, well, how come I don't try making it a decimal? Since our nth term is listed as a fraction, right? Our formula has a fraction. That's why I want to leave it as a fraction. Okay, fourth term. 2 to the 4th over 4 factorial. Well, 2 to the 4th power is 16. And then on the denominator, 4 factorial, you guessed it, 4 times 3 times 2 times 1. And if I multiply that out, I get 24. And that will reduce to 2/3. So when we get done and we put the list together, it's not such an obvious pattern, right? We got 2, 2, 4/3, 2/3. But if you look at how these were created, if you look at the tops of the fraction, we had a 2 and then a 4 and then an 8 and then a 16. So the top of the fraction just kept doubling. And then on the bottom of the fraction, whenever we do the factorials, we're just multiplying by the next number. Right? So there is a pattern about it, but when you look at the simplified answers, you're like, whoa, this just looks kind of weird. Do we have another? Surprise, surprise. I bet this is going to spell worksheet once again. And state parks are beginning to reopen in places. And if you're willing to drive a bit and get away from the Puget Sound region, you can find that not only are some of these state parks open, but social distancing is not an issue. This is Lake Lenore Caves State Park in eastern Washington, and that's my wife, son, and daughter. This is not from this year, this is from a previous year, but we've kind of got our eyes looking at this one, thinking this summer, if we want to do some hiking, our opportunities, we figure, are going to be far from the metropolitan centers.